This clip looks at finding the center of mass or centroid of a region. We've talked about the idea of doing a centroid when we have simply a function that's bounded by the x-axis, but what if we have a function or a region that's bounded by two different functions? The principle is still the same. If you remember, when we looked before at how we calculated the weighted average, whether it be grades or point masses on a teeter-totter, it's kind of the same idea here. We're taking the numerator is basically going to be a weighted average. It's going to be the weighted pieces of it, and then we're going to divide by the total. So in the numerator, you'll notice we have a weight or a mass times a position, so m times an x. And we're going to do the same thing here. So if you recall, when we're talking about the x direction, we pick an arbitrary little spot here, and the area of the rectangle represents kind of the weight or the mass of it. And so we need to find out where for a given x location, where the center of that will be. Well, of course, along the x direction, it's going to be simply in the midpoint in between those two. So we just use x. So we'll assume we center these guys at x. So we now need to figure out what the weight of it is. And notice that the rectangle I've just drawn is going to have more weight to it in terms of influencing the center of mass than, say, this little one down here, because it's bigger. Okay, it has actually more area. So we're going to use the area to represent the weight. So again, what we're going to do is we're going to talk about connecting these two things in the way of the location times the weight or the mass of that object. And then we're going to add those pieces up. So in this particular case, for the x, we're really looking at having a combination of the location, in this case x, so we'll call it little x sub I, and then we need to figure out what the mass is. Well, the mass or the weight really is the area of it. So this dimension right here is my delta x, and this distance here is going to be the difference between the two functions, in this case f minus g, the way I have them labeled. So this would be f of x minus g of x. Okay, so we have two dimensions to get the area of this. So this is simply going to be f of x sub I minus g of x sub I times its thickness, which is delta x. So if we want, we can actually write it and distribute the x sub I through. So this is going to be x sub I f of x sub I minus x sub I g of x sub I, that whole thing times delta x, and then we simply sum those guys up. Well, when we take delta x going to 0, or in other words, infinitely many little rectangles, we actually yield an integral. So this guy simply becomes the integral from a to b, x times f of x minus g of x dx. Now that's just the numerator part. So now we divide it by the total, quote, mass, which is simply the area under the curve. The total area under the curve, which is just going to be f of x minus g of x dx. And so that gives us the x-coordinate of the center of mass. Now we can do the same sort of approach when we're talking about the y-coordinate, except the center is going to be located in a slightly different place. So let me do another sketch here real quick. So suppose, again, got a couple functions. Label them with different colors so we can see. Suppose that's f. And let's suppose this guy is g. All right, now we're going to take the same thing, except for a rectangle in here, we're looking at where the y center of mass is. So that's really going to be halfway up the y coordinate. It'll be somewhere in here, if I can draw it properly. But it's going to be basically halfway between F and G. Well, how do you find the midpoint between two things? Well, you simply average them. So if this is my place X, I'm really going to look at averaging these guys. So that's going to be f of x plus g of x divided by 2. Or in other words, 1/2 f of x plus g of x. Okay, so that's the location. Pardon me, not spelling right today. So that's the location in the y direction. Okay, so now, just like we did before, we're going to take the location times the area of it, because the area represents the weight or the mass of the region. And so I'm going to sum these guys up for a given little x sub I. I'm going to have 1/2 f of x sub I plus g of x sub I. That's the location. Now I have to multiply by the weight or the mass of it. And again, that's the same as what we had before. Right? The weight or the mass is still going to be that expression right there. So this is going to be times the difference in the heights. Okay, that gives the height of the rectangle, times delta x, which gives the width of the rectangle. So this is the weight. All right. Now, the one thing you'll notice is if I multiply the two binomials together, the f of x sub I plus g of x sub I and the f of x sub I minus g of x sub I, you'll recall from algebra class, that's going to be a difference of squares. So that means I'm going to end up with a sum of 1/2 f of x sub I squared minus g of x sub I squared delta x. So as a result, as I take the limit, as delta x goes to 0, this guy becomes an integral from a to b, 1/2 times the quantity f of x sub I squared minus g of x, oops, I don't need these sub i's anymore because I'm taking the integral, g of x squared dx. And so as a result, that's just simply the numerator portions. So now I divide by the total mass, or the total area, so to speak. So that's just the integral from a to b. Again, f of x minus g of x dx. And that's going to be the location of my y-coordinate of the center of mass. Okay. So we end up with the same idea. It's just now we're looking at, in the x and y direction, figuring out where those center pieces would be for each strip.